Hopefully it is recording. Yeah, good morning to you all. So yesterday we were discussing about the surface drainage system design, and which contains basically the two steps. The first step is to determine the peak flow expected from the drainage area, mostly the surface. We're talking about the surface. So how much overland flow you're going to expect from the given area. So that is the hydrologic design. Whereas once we know the peak flow expected from the area, so that is the, I mean, maximum capacity we expect, and accordingly, a, a shallow or a deep ditch is being designed. That is hydraulic design. Okay, so the two designs it contains. So today we are going to talk about the design of subsurface drainage system. So let's put subsurface drainage system design. Okay, so in this, so the basically to design either deep ditch or the pipes. So it basically involves design of deep ditch and or design of pipe. So pipe means is the tail pipes. Okay, so that means if you have the land surface like this, and so suppose this is an impervious layer. This one. Okay, and when you have the recharge, which is going down, and because there is impervious layer, and so suppose there's a groundwater which is there. Okay, this is the water table, groundwater table. So when the recharge, let's say the Q, it continuously, when it is adding continuously, so the water table is going to rise, right? Slowly it's going to rise like this, and then finally, it will be on the surface. Okay, because this is an impervious layer, and there's a water table which is sitting on impervious layer, so there's no possibility that water will go beyond the impervious layer. Okay, so the only way is to accumulate upwards. So that's what's going to happen, right? So, but since you're planning for crop growth, so you need to remove this water. Okay, so that's why either you use the surface water, surface, drainage designs. So in surface, you got the shallow ditches, only the, the water which is accumulated above the surface can be removed. But from the root zone, suppose for example, your root zone is somewhere here. So in order to remove, either you have to use a deep ditch, okay, or you can use the tiles, which is underground pipelines. So this is the tiles, okay. So either you design, deep ditch, or you design a pipe in this case. So this since it is inside the surface, so we call the subsurface design. Okay. So what are the requirements? Okay, so what are the requirements in order to design? So before designing, so you need to have some information so that what should be considered in the design. Okay, things to be considered or followed. Okay, so there are basically 8. So let's summarize that. Again, we'll show this schematically. So suppose this is your land surface and there is an impervious layer. Okay, and assume that there is a crop. Okay, which is there. So, and what do you call? So this is the root zone, crop root zone. So this is the root zone. Now the first thing what you have to know is the soil information. The first number one thing is soil info. So what is that soil info? So what is the soil type? And then aquifer characteristics, what kind of aquifer the area has, and then groundwater quality. Okay, so groundwater quality. Okay, so these things first you need to consider. So since you are installing, the pipe drainage system or any subsurface drainage system, so we should know what kind of soil type, what kind of soil is. So that whether it is sandy soil, clay soil, so based on that, the spacing and will be decided. Okay, because what we are doing, we are draining the water. Okay, so it all depends on the media. So the media here is the soil. So you should know the soil characteristics and also the aquifer. So whether it is confined aquifer or semi-confined aquifer or unconfined aquifer, all those things we need to consider. And groundwater quality, of course, since one of the objectives of subsurface drainage system is to remove salts, so the groundwater quality is definitely important. So this is number one, and number two, the irrigation water quality. Number two is irrigation water quality, right? So this is number two because irrigation water also contains sometimes salts. So make sure that you are irrigating with, uh, irrigation with the salt content, with the acceptable limits. Okay. So if it is more, then that's going to accumulate salts. And third is, source examination. So what is the, so third is the source of excess water. So source of excess water. Right, so that's the main issue. So what is the source of excess water? Is it irrigation? Is it the rainfall? Right? So you need to identify, so what is really causing, or is it the lateral flow from other fields? Okay, so that is the source of excess water. And fourth is, climatic data or climatic parameters. So climatic parameters, because that defines how much water is being evaporated or through evapotranspiration. So it's lost through evapotranspiration, right? And what is the precipitation? So all that information you need the climatic data also. And fifth is the crop, about the crop, fifth. Okay, so that is what kind of crop and cropping pattern. So cropping pattern, so in a year, what is the sequence of crops you are planning? Like, in Kharif, some might be planning, rice, followed by wheat, followed by another rice, or, um, maize, right? So this kind of cropping pattern, you need to understand. Based on that, the root zone depth will vary, so different crops. So accordingly, you have to think, so what is the optimal, depth of, the drainage base for this particular area. So the crop and cropping pattern is important. And then sixth is uh, the hydraulic conductivity. Okay, so hydraulic conductivity of soil. So that, that is denoted with K. So this is important in order to, understand the flow. Okay, so hydraulic conductivity of soil. And then seventh is the drainage coefficient. So you know the definition of drainage coefficient. So the depth of water drained from that area in a day is called drainage coefficient. So this is very important, drainage coefficient, so that, based on the water balance, right? So what you're expecting, what is the drainage coefficient you're expecting, or what is the drainage depth will be, you're expecting from that particular area in a day. So that is drainage coefficient. And then eighth is, drainage depth. Or drain depth. Okay, so here the drain depth means, suppose you're installing, so if this is the root zone, this is the root zone. So obviously the drainage system should be installed just, below the root zone system. Okay, root zone, so that the water from the root zone will be emptied efficiently. Okay, so suppose if your drainage, this is the pipe drainage which is installed just below the root zone. Okay, so if this is the drain base, so drain base, so that means water will be expected at this level. This is the drain base. Okay, so the distance from top to this drain base is called drain depth. So this is the drain depth. Okay. Okay, so the drain depth is important. All right, and also the spacing between the drains. So drain, these are all design parameters. I'm talking about finally the design parameters, drain depth, the spacing between the drains, okay, and the pipe, type of pipe and pipe section, that means diameter and all, okay, and then envelope. So once you install it in the soil, once you install the drain pipe in a soil, so in order to avoid the blockages, because the sand contains, smaller, tiny particles, clay particles. So since the drain pipe has, the holes, perforations, so that should not be blocked. So that's the reason you need to put an envelope. So using an envelope material, it could be like a gravel, or it could be like a synthetic material, right? Um, So using nylon and all other things, so it creates some kind of protection from the the particles, sand particles to enter. Okay, so that your drain pipe won't be blocked. So this is envelope. This is the drain pipe. Okay, so at least you need this information in order to design a subsurface drainage system. So the first thing is, so the first is the soil information. Second, about irrigation water. Then source water, sources of excess water, climatic data, information about the crop you're growing, and soil hydraulic conductivity, and of course the drainage coefficient, and the design parameters like the drain depth, spacing, pipe section, envelope, and all other things. Okay, so this much information really you need to have before going for the design. Okay, so after having enough research, the United States, called the United States Bureau of Reclamation, so that the United States Bureau of Reclamation, right, USBR, they recommended the drain depth should be 2.4 meter from the surface, right? So this is the recommendation. So 2.4 meter from the surface. For mostly this is for farmlands. Drain depth should be 2.4 meter from the surface. So I mean, if you don't have any information, then you can use this data, but otherwise we can design by having enough data. Okay, so estimation of drainage basically requires the following. So estimation of this drainage requirement. Estimation of drainage, let's say the coefficient. How do you estimate the drainage coefficient? So that is, let's say mm per day. So again, the drainage coefficient means you have a drainage system installed, let's say. So in a day, what is the depth of water you are getting out from the drainage system in a day? So this is a specific, okay? So that's a drainage coefficient. How do you estimate that? So the first thing is you should have the historical weather data. So weather data that includes the precipitation, evaporation, and evapotranspiration. Okay, so these three information is, and also the runoff from the area. Okay, so knowing this, you can use the water balance equation, right? So suppose this is the area you're expecting, and you know the precipitation. So this should be the daily. So because we are calculating for daily, so you should have daily average values. Okay, historical daily average values you should get. So the precipitation and the evapotranspiration, or maybe evapotranspiration if you have a crop. If you don't have a crop, evaporation. Okay, and then what is the runoff? Okay, and then this is, you assume that this is the drainage. Okay, this is the drainage. So water balance, according to water balance equation. So drainage, the Q So let's say the precipitation is equal to evapotranspiration plus runoff plus this drainage. Okay, so now Q is equal to P minus ET minus R. Okay, if you know the daily historical values, let's say the 10 years, 10 years, you average, day number 1, right, for precipitation. For precipitation, you take 10 years daily and average them. Similarly, for ET, so 10 years daily, average them. So similar, so that's why you get Q is equal to, this is the daily mm per day. This is also mm per day, and this is mm per day, and this is mm per day. So once you have the daily values, you can calculate what is the daily Q you're expecting from the particular area based on the historical data. Okay, this is important. And then the next is, so estimating the drain spacing. The first thing is, so once Q is known, so how to estimate the drain spacing? So the spacing between the two drainage pipes. Okay. Estimating drain spacing. Okay. So before that, let's understand some terminologies. Okay. So the terminologies here are for this one and this one. So this is an impervious layer. Okay. And you have the crop here, let's say. So this is the crop. And let's have this is the root zone. So these terminologies should be understood very well. Okay. And then, so excuse me. So let me just go and talk to these guys. It's noisy. Hey, Dada, just wait कर class चल रहा है. हाँ, बहुत आवाज आ रहा है. हाँ, हो गया. Sorry. Okay, so this is the land surface on top, and so this is the root zone. So our intention is, so the water level or water table should go below the root zone. Okay, every time. So even if there is a heavy rainfall, so that should not be, within the root zone. So that should go away from the root zone. So let's assume that you are installed a pipe drainage system here, just below the root zone. Okay, so I'm taking a two pipes. This is sectional view. So you take a section. So this is one pipe. There is another pipe. And similarly, there are series of pipes installed. Okay, you take a section. I'm just considering, the two pipes. Okay, and if you see the what happens? Suppose you have a tank like this, right? Assume that there is a tank. Soil is not present. Okay, so the completely empty box. So once you open, so let's assume that the water is flowing from this drain and this drain. Okay, so from two drains, water is moving. So initially the water table would be somewhere, let's say this is the initial water table. So in that case, there is no soil present, so water is going to fall equally, right? So there is a layer, I mean, the water level, let's assume that there's a straight line. Straight line water level will fall down, constantly. right? So that we would see. But what happens if there is a soil inside? If there is a soil inside, you won't see the, the straight line of water table which is falling down. So you would see a curve like this. So this is, instead of straight line, you would see a curve. Okay, so this we call a drawdown curve. Okay, or this is, total head curve, total head or gradient curve, this one. Okay, you must understand this, why this curve is coming. Because, and also the nature of curve will depend on the soil to soil. Okay, because that creates, the voids. Different soils will create different voids. Okay, this is the drawdown. So, and this is the drain base we call. This is the drain base. So that means even if there is no recharge, so you would expect, the drainage base. So drainage base means water will be expected just above this line, just at this line, even if there is no recharge. Okay. So that is one. So the distance between the surface, the distance between the surface to the drain base. So from here to here, so this is denoted with W. This is denoted with W. So this is a drainage depth, called. And then there is a distance from the impervious layer to the drain base, that is denoted with capital D, right? So that is depth to impervious layer from the drain base. Okay, and then we have from the top side. So this is the middle. If you see, so this is the middle point. This is the middle point, which is exactly the same, just like a mirror image. If you see this side, left side and right side, so exactly they look same. So this is a theoretical model. We assume that the soil is, homogeneous and the properties are isotropic. Okay, so then you would see the curve like this, exactly symmetrical. Okay, so in that case, the distance from the midway. Okay, so this we call capital H. So capital H is water table depth. This is the water table depth midway between the drains. Okay, so the midway between the drains. So this is a drain, and this is also a drain. So this is the midway between the drains. So water table. This is a drawdown curve, or this is also water table you have. Okay, this is a water table. So H, capital H is the water table depth midway between the drains. So from here to here, we are denoting with small h. Okay, so from drain base to above the water table, so that is denoted with h. Okay, I think this much you must understand, and also the important thing, the spacing. So spacing is, so this is the spacing between the two drains, that is denoted with capital L. Okay, and the drainage, that is Q, is the drainage depth. Okay, drainage coefficient, you can say that's Q, mm per day. Okay, all right. So important parameters are W, D, H, small h, and L. Okay, so you have to keep in your mind, these are the basically the the terminologies we'll be continuously using. Okay, so I will also write down here so that it will be easier to remember. So capital W is the drainage depth or drain depth. Capital D, this is the depth to impervious layer from drain base. Okay, H is water table depth midway between the drains, and small h, which is also capital W minus h. This is the water table height. Okay. All right. So the basically, if you see a schematic view of how to estimate the drain spacing in simple way, schematic representation of estimating drain spacing, that is L. So you need a Q value, that is drainage coefficient, and you need a H value, which is the water table height from the midway between two drains from the surface, that is capital H, and W is the depth to drain base from the surface. So from capital H and small h, you can estimate small h. Capital H and W, you can estimate small h. So the small h here is W minus capital H. This is what you get. And if you know the Q and small h values, so then you have a drain spacing formula. So the drain spacing formula is a function of Q and small h. And also it requires the two parameters. One is the drain type, mostly the pipe characteristics. Okay, drain type, and other information is soil type, soil parameters. So hydraulic conductivity and all other things, parameters. Okay, only that much. And then you get capital L. Okay, so these are the inputs, and this you have to estimate, and this you will be, and this will be estimated. Okay, and for that you need a drain spacing formula and the other information. So our aim is to find out what is the drain spacing formula now. Okay, so what is the drain spacing formula? We are going to find out. Okay, so before that, so let's just look at the the flow pattern in case of subsurface drainage system. So the flow patterns in case of subsurface drains. Okay, I mean, let's compare real and how we are going to uh, take it as in theoretical way, so that we can define or derive an equation easily. Okay, so this is the land surface, and this is an impervious layer, and let's have this is a one drain pipes. So this is the two drain pipes, and this is the drainage base. Okay. So I'm going to separate these into two pieces. So one for real and one for for theoretical purpose. Okay, this is, let's say this is a in a real field how the pattern looks like, and this is like a schematic. This is for our deriving equations. So how we are making the complex things into simple so that the derivation will be easier. So L is your the length between two drains. Okay, and this from top to drain base, capital W, and from these two impervious layers, capital D. Right, and then you would expect a water table. So this drawdown water table will be like this. So since it is the soil media. So in the real field, if you observe the flow patterns, so if there is a recharge, so it would directly goes down here. This is the recharge. So let's say there are three points, let's say. And this would also go directly from here. And this would also go directly from here. Okay. And then once it reaches the drain base, it's going to take a, a circular path like this. So this would have been happened in reality. Okay. But in theoretically, what we do, we are going to make it into, three flow paths. Okay, the first, similar to the real, there will be vertical flow down. Then after that, instead of taking, the radial from here, first it takes in horizontal. Okay, and then from here, from here vertical, it will be down, and then horizontal, and then we have a radial. So similarly, a vertical little down, and horizontal, and radial. So vertical, little down, horizontal, and radial. So instead of having vertical and radial, so you'll have the horizontal flow component in case of schematic. So the horizontal flow, if you see, this will be like the flow will be like I mean the horizontal will end exactly in a circular. I mean the circumference of the radial flow. Okay. So here there is some assumptions. This will be like a 0.7 into D, and the horizontal flow is restricted up to L/4. Distance from drain base to down. So you would expect horizontal flow till L/4 distance. Sorry here. So this distance. Yeah. So this distance would be L/4. So this is what you expect the horizontal flow is in this one. Okay. So in summarizing these, in the real versus schematic, so in real field, you get a vertical flow and also the radial flow, right? So the flow paths, would be difficult to simulate. So that's why we are making this one radial flow into the two, one horizontal as well as the radial. So in this schematic case, the theoretical models, we are going to make like a vertical, horizontal, and radial. So these three flows will be, considering here. So vertical and horizontal. So this would be like below and above the flow paths. Whereas the radial will be vertically towards the pipe. So this is towards the pipe, radial flow. Okay. So now let's find out the equation for the the spacing between the drains. That is one of our the tasks here. But before that, what happens? Suppose if L is how to differentiate whether it is vertical or horizontal, radial, theoretically. So when the length between the two drains is very, very smaller than small h. Small h means from the drain base to the water table, the midway. So the water table height. So in that case, the L is very, very small. So H is shooting up. So that means vertical flow is dominating here, right? In this case, the vertical flow dominates. Whereas L, suppose if greater than H, so H is very, very large compared to H. So L is very, very large compared to H. So in that case, the horizontal flow dominates. So we don't exactly what is the length and H, but if you think that okay, small H is very, very small compared to the length, so then we can consider it as a horizontal flow. And when if you see L is equal to H, then it's a radial flow dominates. Okay. So the total head loss in this sense, if you see this, so this is the shape. So whatever the shape you're getting, this is the head loss due to head loss. Okay, so the head loss here, the total head loss, which comprises these three or in addition four, head losses. It has four head losses, comprises the total head loss. So whatever you are seeing here, so if this is the x direction, right? And if this is h, x and h, so from here to here you get all h's, right? All h's. So the h's, so that depends on that's the head loss basically. So that the total head loss h will be combination of vertical head loss, horizontal head loss, radial head loss, and there is another one, entrance loss. Entrance loss in the sense here, if, if, if I remember correctly, so in the beginning, I introduced the envelope, right? So the envelope, the water which is entering here, so may not be going, freely. So there is some obstruction. So that is possibly due to the losses which could be, incurred by the envelopes. Okay, so the total H, whatever H you are looking at here, so that will be basically a sum of vertical head loss, horizontal head loss, radial head loss, and entrance loss. So all these in combination. So we are going to see one by one to estimate what is HP, what is HH, and what is HR, and what is HE. Then finally we'll find what is H. Okay, so let me see. So how to find out this vertical? So let's say vertical flow. So let's say A. This is the vertical flow, and we are finding out the vertical head loss HV. Okay. For a vertical head loss, so let's have, we will be using, this is the saturated media. So that's why we'll be using Darcy's equation in order to find out the HV. Okay, so this is the land surface, and you have, this is the impervious layer. Okay, and let's assume that there is a drain which is sitting here, and this is the drain base. I am taking halfway of the drain base, right? So there is another drain point or the drain pipe which is located in the same line, in the same distance. Let's say the distance here is L by 2. This is the L by 2. Okay, so I'm considering it as a symmetry. So I'm taking only half of the drain spacing. Okay, so then after that, what I did was I put a piezometer here exactly at the center. So you all know what is the the purpose of the piezometers, right? So the piezometers basically to install to know the water table depth. Okay, so then just nearer to this, very close to the water table, I put another piezometer. This is the second piezometer, and in order to capture the radial flow, so I would put a piezometer exactly at 0.7 d distance. Okay, so this distance is 0.7 d. Okay, so this is the first piezometer, second piezometer, third piezometer. So these are the piezometers. Okay, and I would expect the water table, in this, it will be like this, because the center. Then after that, the same thing will be reflected. So it's like a mirror image. Okay, so whatever water table I'm looking here, and so this one, this is the level, and you would see this is the level for horizontal. So the difference between these two will be, that is HV. Okay, so the HV is not, so the second, so one is installed exactly at the midpoint, second is installed just close to one. Okay, so we exactly at the center, we expect 100% vertical flow down. Okay, exactly at the center. So that's why, so the difference, what you get from 1 and 2, the piezometers. So you have the water table height here, you have water table height here in the second piezometer. So the difference will be HV. So that will be the head loss due to vertical flow. That one. And so if this is the dV, so let's say this distance from drain base to this one, this is dV. So dV is, so dV is from the surface to drain base. Okay, so that's the let's say the dV. I put the drain base. This is the drain base. Okay. All right. So then Q is your recharge. That is the Q. That is mm per day. That's Q. So now how to use? So yeah, from here to here, this is the D. Okay. So I just want to, so the water table, water level here in second, and the water level in third. Okay. So the difference between the water levels in the second piezometer and third piezometer will be, this is HH. This is a horizontal. And if you have the, and if you have the water level here and the piezometer here, so this will be your HR, that is head loss due to radial flow. So head loss due to radial flow. So you have practically, so if you install 3 piezometers, you will get this HV, HH, and HR. So, but theoretically, we are going to formulate it. That's what we are doing it here. So now for HV, I'll be using the Darcy's equation exactly at the center. So I'll take a small section from the center. So let's assume that if I take a small section from the center, so this will be dV. and I have the, there's the 2 points. I have the pressure difference, that is HV. Okay, and this is the Q which is going down and Q which is going out. Okay, so now if you use the Darcy's equation, so Q is equal to hydraulic conductivity into HV divided by dV. Okay, this is, so Q is equal to KIA. Okay, so this is the flux, so it's already A is divided, and HV by dV is your hydraulic gradient. Okay, this is your hydraulic gradient. So now HV is equal to Q into dV divided by K. Let's say this is the K is your hydraulic conductivity of this material. Okay, so this way you can estimate the HV. It's already 10:58. Okay, so the Q is the recharge, so I'm going to just define these terms. So HV is the vertical head loss, let's say head loss due to vertical flow, and Q is the water flux, or let's say, what is this, recharge or recharge. So this will be your in depth units, that means meter cube per meter square. This will be in the depth, and K is the hydraulic conductivity, and then dV is depth to drainage base from the center, from the surface at the halfway between the drains. Okay. All right. So I'll stop here. So if you have any questions, let me know. So whatever this thing we got, so this is from, yeah, this is exactly from this part. So I'm just taking a little bit of, a segment from there. So Q is adding on top and Q is coming down. This is the vertical flow, and K is hydraulic conductivity, and dV is your total, soil mass. So dV will vary. Okay, so dV will change with your water table. Okay, and HV. Okay, so the HV. So this is the theoretical model. So it all, once you put everything together, so it will take the influence of different parameters. Okay, once you put all HV, HS, and HR and HE values as a capital H, so that will take care of all the the little changes in the parameters. Okay. Yep. Any questions before I close? Otherwise, see you all next week. Yeah. Take care. Bye bye.